The development of magnetic resonance imaging (MRI) for cancer detection has a complex and debated history, marked by significant contributions from multiple research groups over the past 50 years. Despite its potential, cancer remains a significant challenge for medical professionals, and the development of nuclear magnetic resonance (NMR) for cancer detection is a crucial contribution of physics to human health. Unlike computed tomography, CT scans, MRI's primary advantage lies in its ability to image the physical state of cellular water, which reflects the physiological-pathological state of biological tissues. A thorough examination of the research record reveals that the development of MRI for cancer detection involved three key steps. First, researchers used spin-echo NMR to measure relaxation times in cellular water. Second, they discovered the sensitivity of NMR relaxation times, T1, T2, and spin diffusion coefficient, D, to the physiological-pathological state of biological tissues. Finally, these findings were applied to cancer diagnosis. The controversy surrounding the discovery of using NMR for cancer detection has been ongoing, with Damadian and P. Lauterbur being two prominent figures in the debate. However, this review aims to move beyond the claims of individual research camps and highlight the critical contributions of multiple research groups. By clarifying the contributions of various researchers, this review provides a comprehensive understanding of the history of MRI development for cancer detection. In the early days of physical biochemistry, there were two contrasting viewpoints on the physical properties of water in biological cells. The traditional view held that cellular water is no different from water contained in a test tube, while a more physically oriented group believed it to be part of a highly structured ion-water macromolecular complex. To resolve this debate, researchers proposed using nuclear magnetic resonance, NMR, to study water in biological tissues. Two major types of NMR techniques were employed: continuous wave, CW, NMR for identifying chemical contents, and pulsed NMR, spin-echo NMR, for measuring spin lattice relaxation time T1 and spin relaxation time T2, which reflect the correlation times of nuclear spins. These measurements were often used for studying the physical state of molecules. During the 1960s, preliminary studies using both CW and pulsed NMR had been conducted on biological tissues, revealing that cellular water appeared to have much reduced mobility in comparison to water in free solution. The author, a PhD student at Rice University, became highly interested in biophysics and collaborated with a young physiologist at Baylor College of Medicine, C.F. Hazelwood. They converted a home-built spin-echo NMR spectrometer at Rice University to study the physical state of water protons in biological tissues. The authors conducted a series of studies on cellular water in different biological systems, finding that the NMR relaxation times, T1, T2, and the spin diffusion coefficient, D, of water protons were much shorter in biological tissues compared to free water, suggesting that the water in biological tissues is more ordered than bulk water. Moreover, the ordering of cellular water was found to be highly sensitive to the physiological state of the biological tissues. Significant changes in T1, T2, and D of water protons were observed during the normal development of biological tissue. For example, when skeletal muscles were stimulated, the T1 and T2 of water protons decreased, indicating increased ordering of cellular water. This observation led to the hypothesis that the physiological state of biological tissues can be monitored by NMR. In a study on muscle cells in rats, researchers observed that the NMR relaxation times of cellular water in less differentiated muscle tissues were significantly longer than those in more differentiated mature muscle tissues, as shown in Table 1. This discovery has important implications, as cancer development is known to be related to dedifferentiation of biological cells, suggesting that relaxation times in tumor tissue may differ from normal tissue. To test this hypothesis, the researchers collaborated with a pathologist to investigate a mouse model of mammary tumor, which offered several advantages, including three well-defined morphological states: normal tissue, preneoplastic nodule, and cancer. The study's results, presented in Table 2, confirmed the prediction that NMR relaxation times in tumor tissue would differ from normal tissue. The findings were first reported in a meeting abstract submitted to the American Physical Society in September 1971 and later presented orally at the 1972 APS March meeting, where it garnered significant attention from physicists. The full paper was subsequently published in PNAS in June 1972. The researchers' use of pulsed NMR measurements to quantify relaxation times, T1 and T2, and spin diffusion coefficients, d, in pure water and mouse mammary gland tissue, provided valuable insights into the potential of NMR for detecting pre-cancer formation in mammary tissue, which could have significant implications for breast cancer treatment. Dr. Raymond Damadian's research at Downstate Medical Center in New York, in 1971, investigated the structural water hypothesis in the context of tissue studies, drawing on NMR work by an unrelated research team without prior NMR training or experience. Using an NMR spectrometer from the NMR Specialties Corporation, Damadian measured the average T1 values in 3 tumor types, observing longer relaxation times in certain tumors compared to various normal tissues. Table 3. Published as a brief report in Science, these findings contributed to understanding the structural water hypothesis, a notion also acknowledged in the press release of the 1972 American Physical Society APS March meeting highlighting Chang et al.'s related NMR study. Damadian's results confirmed the feasibility of NMR in detecting longer T1 values of cellular water in specific tumors versus normal tissues. Notably, these investigations have broader implications for diagnostic medicine. A thorough grasp of proton relaxation times in tissues holds promise for new medical diagnostics, with this area underscoring a growing awareness of the diagnostic value in this approach. While comparing relaxation times can offer crucial distinctions, work such as this stresses understanding different variable sample temperatures and a generally constrained nuclear relaxation dynamics influencing hydrogenous substance longitudinal spin lattice, T1, time, average full, field-wide pulse, 1 full sampling time. Using applied sequences applied sampling regimes, street period sets a lot via measurements field spatial var settings given varied regions investigated then getting proper experimental. This section of the research paper presents the findings of a study on the use of nuclear magnetic resonance, NMR, as a diagnostic tool for cancer detection. Building upon previous research by Damadian and others, the authors measured NMR properties of cellular water in the same tissue model, breast tumor, at 3 different morphological states: normal tissue, preneoplastic nodule, and cancer. This allowed for a clear correlation between changes in NMR parameters and different stages of cancer development. The authors measured not only the spin lattice relaxation time T1 but also the spin-spin relaxation time T2 and the spin diffusion coefficient d of water protons. They found that all 3 NMR parameters undergo progressive changes during cancer development. A major discovery of the study was that NMR properties of water protons start to undergo distinct changes during the preneoplastic stage, suggesting that NMR can be used as an early diagnostic tool. The authors' findings have stimulated further research in the field, including studies by Weissman and Hollis. Hollis' study, in particular, highlighted the importance of using multiple NMR parameters to develop NMR as a diagnostic tool, which was a key aspect of the authors' earlier study. The authors' subsequent studies have further demonstrated the potential of NMR for detecting cancer, including the ability to differentiate between normal, precancer, and cancer cells in human breast tissue with high statistical significance. The results indicate that NMR relaxation times can distinguish between breast neoplasms and other diseased or normal tissues with high confidence. In the early 1970s, scientists began to explore the application of magnetic field gradients in generating 2D images from NMR measurements. This was stimulated by the growing knowledge of X-ray, QUART, imaging techniques. Paul Lauterbur proposed a method called zygmatography, which involves scanning a sample along one axis and then rotating it for scanning along other axes, resulting in a 2D image of the distribution of water protons. Peter Mansfield, a British physicist, was also interested in applying magnetic field gradients to generate 2D scanning images for solid-state physical samples. Damadian, another active player during this period, invented a magnetic imaging method called FONER, and filed a patent application in 1972 for a whole-body NMR machine for cancer detection. He published the first human thoracic image using NMR in 1977. These works stimulated many other laboratories to rush into the development of magnetic imaging, with most images based on NMR measurements of spin density, or the concentration of water protons. Although these images were crude, they were published mainly for the purpose of competing for priority record. The early 1970s witnessed the inception of NMR imaging, with pioneers such as Lauterbur, Damadian, and Mansfield contributing to its development. Their efforts led to the creation of various magnetic field gradients, which significantly enhanced the quality of 2D scanning images. However, these images were still not as clear as those obtained through X-ray CT scans and lacked sufficient anatomical details. A breakthrough came in the early 1980s when the next generation of NMR imaging devices began utilizing spin-echo NMR to measure the relaxation times of tissue water at different locations within biological samples. This shift in focus was driven by the discovery in the early 1970s that NMR relaxation times are sensitive to the physiological pathological states of tissues, allowing for the differentiation between normal and pathological tissue states, particularly in identifying cancerous tissues. The diagnostic value of MRI increased significantly with this new approach, making it more useful than CT scans. Consequently, the medical radiologist community decided to change the name, NMR imaging, to magnetic resonance imaging, MRI, to dissociate it from nuclear radiation, which could evoke negative associations in some patients. From the early 1980s onwards, MRI became a highly active research area in medical physics, with major hospitals beginning to acquire MRI machines. High-quality images were generated, marking a significant milestone in the evolution of MRI technology. Following the 1980s, the development of MRI was significantly enhanced by several technological advancements. These included the availability of affordable and powerful computers for image processing, the spin warp technique which greatly sped up the MRI measurement process, the supply of superconducting magnets with large bore, and the development of paramagnetic agents such as G-based contrast agents that greatly enhanced the contrast of MRI images. These advancements led to MRI becoming a routine diagnostic tool for radiologists to detect tumors in patients, providing clear anatomical details. However, a controversy arose between Paul Lauterbur and Raymond Damadian over the invention of MRI for medical uses. Lauterbur omitted to mention Damadian's work in his 1973 Nature paper, leading to a common misunderstanding that he was the principal inventor of MRI for medical purposes. This misunderstanding sparked a bitter rivalry between the two scientists, with Damadian establishing a commercial company, Fauner Corporation, in the late 1970s and producing the first NMR image of the human chest in 1977. Both Lauterbur and Damadian moved between different social worlds to develop MRI and strengthen their priority claims for its invention. In the development of MRI for cancer detection, three major groups made significant contributions: the Damadian group, the Baylor-Rice team, and the Lauterbur group. The Damadian group discovered that NMR relaxation times, such as T1 and T2, and the spin diffusion coefficient D, are sensitive to the physiological pathological state of biological tissues, enabling distinction between cancer and normal tissue. The Baylor-Rice team contributed to the use of spin-echo NMR for relaxation time measurement in biological tissues, while the Lauterbur group introduced magnetic field gradients for 2D scanning. Contrary to popular belief, Lauterbur's zygmatography, although groundbreaking, was based on continuous wave NMR and measured spin density distribution, but not aimed at distinguishing cancer from normal tissue. Damadian's work, on the other hand, focused on the physiological pathological sensitivity of NMR relaxation times and spin diffusion coefficients, making it essential for diagnostic MRI. Despite Lauterbur's Nobel Prize in Physiology, Medicine in 2003, a careful examination of the published record reveals that his work did not involve spin-echo NMR nor measure the position dependence of water proton relaxation times. Moreover, the 2D scanning of spin density in original zygmatography was not intended for differentiating cancer from normal tissue. The MRI community remains polarized between the Lauterbur and Damadian sides, with many latecomers lacking the time to carefully examine the publication record. In reality, Damadian and Lauterbur made different contributions to the development of MRI. The use of spin-echo NMR for relaxation time measurement, the discovery of the sensitivity of T1, T2, and D to physiological pathological states, and the application of magnetic field gradients for 2D scanning were all crucial steps in the development of MRI for cancer detection. These contributions came from multiple scientists and should not be overshadowed by the rivalry between Lauterbur and Damadian. Nuclear magnetic resonance, NMR, has a rich history in cancer detection, dating back to the pioneering efforts of C.F. Hazelwood, D.C. Chang, R. Damadian, and P. Lauterbur. Between 1969 and 1972, Hazelwood and Chang conducted continuous wave NMR, CWNMR, and spin-echo NMR studies, observing significant differences in NMR relaxation times T1, T2, and spin diffusion coefficient D between bulk water and cellular water. These differences indicated a form of ordering in cellular water, which depended on the tissue's differentiation state. Less differentiated tissues exhibited longer relaxation times, suggesting that NMR could be used as an early diagnostic tool for identifying pretumor tissue. R. Damadian's 1971 science paper reported measurements of T1 relaxation times in 6 normal rat tissues and 2 malignant solid tumors. He found that the relaxation times for the malignant tumors were distinctly different from those of normal tissues, while benign fibroadenomas had T1 values similar to muscle. This implied that NMR could differentiate malignant tumors from normal tissues, although the differentiation of benign tumors remained unclear. Damadian filed a patent application in 1972 to build an NMR machine for cancer detection. P. Lauterbur's 1973 Nature paper introduced NMR zoogmatography, which utilized 60 MHz radiation and a static magnetic field gradient generator to generate 2D images of nuclei distribution, primarily water protons. Although this study did not involve biological tissue, it laid the groundwork for further exploration into NMR's potential as a diagnostic tool. Lauterbur cited Weissman et al.'s paper, which referenced Chang et al.'s 1972 APS abstract. These pioneering efforts established the foundation for NMR-based cancer detection, focusing on relaxation times, tissue differentiation, and nuclei distribution. The research paved the way for further investigation into NMR's potential as a diagnostic tool, with significant implications for early cancer detection and treatment. The development of magnetic resonance imaging, or MRI, is a prime example of the significant impact of physics on medicine. This innovative technology, born from interdisciplinary research, has revolutionized the field of medical imaging. Physicists, chemists, physiologists, and pathologists work together to create a diagnostic tool capable of non-invasively visualizing internal structures. The 2003 Nobel Prize in Physiology or Medicine, awarded to Paul Lauterbur and Peter Mansfield for their MRI discoveries, sparked controversy due to the exclusion of Raymond Damadian, another key contributor to the technology's development. Despite this debate, the importance of interdisciplinary research cannot be overstated. The convergence of knowledge from various fields has led to groundbreaking advancements in medical imaging. Physics, in particular, has played a crucial role in the development of MRI, providing the scientific foundation for understanding the behavior of atoms in magnetic fields. The potential benefits of physics in medicine are vast, with applications extending beyond MRI to the treatment and understanding of diseases. By harnessing the power of physics, researchers can develop new diagnostic tools, improve existing treatments, and unlock the secrets of human biology. The collaboration of scientists from diverse backgrounds is essential for driving innovation and advancing our understanding of the human body. This paper highlights the significance of interdisciplinary research, emphasizing the need for continued collaboration across fields to drive scientific progress. By exploring the development and impact of MRI, we can better appreciate the transformative power of physics in medicine. This research paper provides a comprehensive overview of the development and application of nuclear magnetic resonance, NMR, techniques in understanding the structure and function of biological tissues, particularly focusing on their role in cancer research. The authors discuss various studies that utilized NMR to investigate the state of water in different types of tissues, including normal and neoplastic tissues, as well as the relationship between spin lattice relaxation times, growth rate, and water content of Morris hepatomas. The paper highlights the pioneering work of researchers such as Damadian, Weissman, and Hollis, who demonstrated the potential of NMR for in vivo tumor detection. These studies led to further investigations on the use of NMR in identifying and characterizing various forms of cancer, including breast dysplasias and neoplasms. Moreover, the authors acknowledge the significant contributions made by other researchers in the field, including Lauterbur, who proposed the concept of image formation by induced local interactions using NMR, and Garraway, Grinnell, and Mansfield, who developed the technique of image formation in NMR through a selective irradiative process. The paper concludes with a discussion on the importance of these findings for future research in cancer diagnosis and treatment, emphasizing the potential of NMR as a non-invasive diagnostic tool. It also recognizes the need for further studies to fully understand the relationship between water content, growth rate, and the state of water in neoplastic tissues, which could ultimately lead to more effective cancer therapies. The development of magnetic resonance imaging (MRI) technology has been a multifaceted process, evolving over decades and involving numerous researchers and innovations. Key milestones in the progression of MRI from its inception to its current applications include the introduction of spin mapping by W. S. Hinshaw in 1974, which utilized moving gradients to achieve nuclear magnetic resonance (NMR) imaging. Shortly after, P. C. Lauterbur proposed magnetic resonance zygmatography, a method that laid the foundation for MRI. In 1977, R. Damadian, M. Goldsmith, and L. Minkoff published the first NMR image of the live human body, marking a significant breakthrough in the field. The same year, P. Mansfield, I. L. Piquet, P. G. Morris, and R. E. Copeland achieved human whole-body Linescan imaging by NMR. W. S. Hinshaw, P. A. Bottomley, and G. N. Holland demonstrated the first radiographic thin-section image of the human wrist using NMR in 1977. R. Damadian also developed the field-focusing NMR (FONR) technique for detecting cancer in tissue, leading to the formation of chemical images in humans. The early 1980s saw the clinical application of MRI, with G. M. Biter, R. E. Steiner, I. R. Young, A. S. Hall, D. J. Thomas, J. Marshall, C. A. Pallas, and N. J. Legg reporting on 140 cases of clinical NMR imaging of the brain. W. A. Edelstein, J. M. S. Hutchison, G. Johnson, and T. Redpath introduced the spin-warp NMR imaging technique, which has been instrumental in human whole-body imaging. More recently, K. H. Z, Q. Wu, H. S. Zhe, and G. Zhu discussed dynamic nuclear polarization as a new methodology and its applications. J. Lorck, T. Frenzel, J. Endrikat, F. C. Alves, T. M. Grist, M. Law, J. M. Lee, T. Leiner, K. C. Lee, K. Nicolau, M. R. Prince, H. H. Schild, J. C. Weinrib, K. Yoshikawa, and H. Peach provided an overview of the development and challenges of contrast-enhanced MRI over the past 25 years, as well as future perspectives. R. A. Kopinen and A. C. Pete discussed the use of MRI and spectroscopy in cancer diagnostics and monitoring, focusing on preclinical and clinical approaches. S. Kleinfeld's book, A Machine Called Indomitable, offers a historical account of the MRI's development, while A. Prasad's work, Imperial Technoscience, Transnational Histories of MRI in the United States, Britain, and India, explores the MRI's development and its implications for identity and authorship in the scientific community.